Hello, in this video I'm going to introduce you to the material for your quiz 9. This corresponds to module 3.2, that is algebraic vectors, and we're going to manipulate them and talk about vector addition and subtraction. And module 3.3 is about scalar multiplication and unit vectors. So the idea is you have seen vectors already, and we want to be able to do operations with them. So we basically have two operations, addition and subtraction, which is basically the same style of operation, and you have the scalar multiplication, which is this one. To be able to add or subtract vectors, what you want is you want to transform them into the algebraic form. So remember that if you have a vector, let me just show you a geometric idea. Remember that to describe a vector, we sometimes refer to it as the initial point and then the end point. So say my initial point in R2 would be the coordinates A1 and A2, and the end point would be, say, B1 and B2. I'm going to put that in quote here as well. So my vector AB will be represented by this. Now, if I want to add vectors, what I need to do is I need to translate this to the origin and write this as an algebraic vector. So what we're going to do is we're going to do B1 minus A1 and B2 minus A2. So really these are the coordinates of the vector that starts in the origin and ends up in this, say, vector V. But the way that we write it is, I'm going to, as a summary of this, I'm going to write it as V equals, and in your textbook, I'm just going to follow the notation there for now. It's going to be as a column, and that's going to be B1 minus A1, B2 minus A2. So suppose that now I have another vector, say my vector U. And I have a similar situation. So U goes from or starts at, say, the point C, which is C1, C2. And the endpoint for U is, say, D1, D1, D2. So similarly, my CD vector would correspond to a U. And just doing the same procedure will give me D1 minus C1, D2 minus C2. And now I am in the position of adding them. So geometrically, adding these two vectors is going to be very easy. If I have this vector here and this vector here and I want to add them, I can just move this vector here. So I copy my vector. Actually, let me put it here because I have more space. So I take this vector, put it here. That will give me something more or less like this. And then adding them would give me a resultant vector that would correspond to this vector. So that's what's going on geometrically. Algebraically, once that I have them in this form, my U and V, U plus V just corresponds, let me just rename this because I don't care anymore about my C's and my D's, so let's call this V1, V2, let's call this U1, U2, and U plus V will correspond to V1 plus U1, and V2 plus U2 in the second entry. So Again, the reason why we need to move this to the origin and present them like this is because once that I have them like this, adding vectors or even subtracting vectors will just happen component-wise. So that means that I just have to look at these entries and add them or subtract them. So that's an introduction of what you should feel comfortable with. Your textbook has a more detailed explanation about this, and it's pretty cool. And the last thing that I want to talk to you about for this video is scalar multiplication. So the idea about scalar multiplication is, say I have my v vector here, and I want to, say, multiply it times 2. So if I multiply times the scalar 2, things happen nicely because the resultant vector that I'm going to get is going to be basically just putting v twice here. If I'm talking about 0.5 times v or half times v, that's going to give me a vector with the same direction as v, but half of its length, and things like that. So everything happens proportionally, with the caveat, and you need to be careful about this, is that if the scalar that I'm multiplying times v is negative, then I have to switch the direction. So, for example, if v is here, minus 2v, or actually, let me just zoom, negative 1/2 v will be like this. So same direction, suppose that with a bit of imagination, that's the same direction, but half the magnitude pointing in the opposite direction as v. And this is what's happening geometrically. What happens if I want to actually get precise coordinates for this? Well, I'm going to do something very similar. If my v started in the point A and had an endpoint B, I do the same procedure as here. So my V ended up being some B1 minus A1, B2 minus A2. And just for convenience, so I don't have to carry all of this notation, let's call it V1 and V2. So if I have C as scalar, so that's usually a real number, but later you'll see that we could have a complex number as well, so real or complex in general. C times V will be just multiplying this C in each of these entries. So that's going to be whatever this number times V1 gives you, C times V2. So as a summary, just remember that you want to make sure to move or to write the algebraic vector, so this form, to transform, no, just to write in the algebraic form of a vector before doing operations. Okay, I'm going to give you a couple of examples more about this. Let me just erase the board and we'll continue. Okay, one of the concepts that we also need to review is if I have V, the vector V1, V2, the magnitude of V is just a number, and it's denoted by these double bars of V, and V is a vector, so let me make sure that I have an arrow that sometimes I forget to put, and that's the square root of V1 square. This should remind you of the Pythagoras formula, and that totally makes sense because remember, these can be thought as the coordinates of V starting on the origin. So if V ended up as V1, V2, this is just the formula of the distance from this point to the origin. So that should totally make sense to you. So let me give you an example of how we would use this one. Two examples. The first one doesn't have to do with this, so we'll revisit this later, but let's start with this first example. So once that you feel comfortable with the idea of using the algebraic vector, expect things that are similar to this. So if I have a vector v that is, say, -12, -1, remember this is my algebraic form of the vector, and say A is the point 7, -7, we want to find B and C such that my vector V, this would be my first part, is equal to the vector AB. And the second question here is that AC equals to -6 times C. Okay. So let's focus on the first problem. I have an A, I have my information for A, I don't have information for B and C. So let's call B just some generic, say, B1, B2. Remember, we are in R2, and we know that because of this information we have two entries. And we're not going to use it here, C, so let me just start with is B, that is B1, B2. I want my vector V, which already I know that is -12, -1. I want this to be the vector AB. And remember that AB would have the form B1 -7. If I write this as algebraic in its algebraic form, and then B2 -7, so B2 plus 7. So you see how we're using the first formula that we saw in the previous page. So we have this, and because I want this to be the same, that tells me that B1 -7 is equal to -12. And if I compare the second entries, this tells me that B2 plus 7 is equal to -1. So from this, in each row, I can just solve. And this tells me that B1 is -12 plus 7, so that's -5. And B2 is -1 minus 7, so -8. So as a consequence of this, I get that my vector B is -5, -8. And sorry, this was a point because remember B is just a point, not really a vector. Okay, so we got the solution for the first one. Let's do the second one. Let me just make sure that I'm not going to confuse my computation, so I can continue here. So for the second part, I'm going to do something similar. Now I'm going to deal with A and some C that I don't know. So let's call C the point C. Remember, it has two coordinates, so let's call them C1 and C2. And similarly, I want AC would be C1 -7, C2 minus 7, so plus 7. I want this to be negative 6 times b. B is negative 12, so positive 72. And negative 6 times negative 1, so that's positive 6. So if I set them equal to each other, what I got is that C1 minus 7 is 72, and C2 plus 7 has to be equal to 6. So C1 is equal to 72 plus 7, so 79, and C2 is 6 minus 7, so negative 1. So that tells me that my point C should be 79, negative 1. So that's the solution for this problem, this example that have these two questions. Let me give you another last problem that has to do with the magnitude. So I'm going to leave this here and tell you how to play around with this and the scalar multiplication. Okay, for this second part, second example that I want to explain to you, we are going to use the magnitude of my vector v. So this is a formula that we saw. And the idea is related to the definition of a unit vector. So what is a unit vector? If I have my vector v here, so here is a geometric interpretation of my v, and suppose that v doesn't have magnitude 1. So suppose that this vector w has magnitude 1. So the magnitude of w here is equal to 1. What is the relationship between this w and this v? For that is we have a nice formula. So the way to compute w is just take v and divide it by its magnitude. So once that I have this, that guarantees that the magnitude of my new vector is 1. Now, if you look at the formula, you can tell that for this formula to make sense, I need the magnitude of v to be different than 0. So you just need to be careful about this. And really, the magnitude of v is going to be 0 if and only if v is 0. So this formula works almost always, except for when my vector is a 0 vector. Okay, so once that I have this, let me apply this to this example. So the example asks, find a unit vector u with the same direction as v, and they are giving me the algebraic form of v. So what am I going to do? Here, my u is playing the role of this w here. So in this case, what I have is that u, because this needs to have magnitude 1, is just going to be my vector v divided by the module of v. Right? Just this formula right here. And this makes sense because this is not the 0 vector, so the magnitude is not going to be 0 here. So what is the magnitude of v? We're going to use this formula, so this gives me 1 over the square root of 36 plus 16 times my vector v, which is negative 6, negative 4. So this is 1 over the square root of 52 times negative 6, negative 4. Okay, so this is perfectly fine, but when you want to compare your answers with the options in the system, you want to always get used to the idea of reducing this as much as possible. So 52 equals 4 times 13. And if I want to take the square root of this helps me doing my reduction. this is the same as square root of 4 times square root of 13, so that's the same as 2 square root of 13. So I am going to use this idea with this. So this is 1 over 2 square root of 13. This continues here, times negative 6, negative 4. And now I can use this 1/2 applied to this, so I end up with 1 over square root of 13 times negative 6 times 1/2 gives me negative 3, and negative 4 times 1/2 gives me negative 2. So this is the form that the solution shows up. Okay, the last thing that I want to mention here is you need to pay attention to the wording, because if they had just say a vector u that is parallel, a unit vector that is parallel to v, that means that I could consider this vector or the opposite direction, and the completely opposite direction would be just with plus signs here. So, but because I want the same direction, I just need to follow this formula as I have it here. And another alternative is that your problem tells you that you want the opposite direction, so a unit vector with opposite direction as your v, and the opposite direction would be just 3, 2 times 1 over square root of 13. So make sure that you pay attention to the wording and the directions. Remember your formulas, and that would be it.